Hi, it's time for another math easy solution. Today we're going to discuss a pretty interesting topic that's looking at hyperbolic functions and looking at an application, which is the catenary function, which is a very interesting and fascinating curve and function that has real-world applications. And in fact, a subscriber of mine has been asking me to cover catenaries for a while now, so I thought might as well jump in right now. So let's look at catenary. So it can be proved that if a heavy flexible cable such as a telephone or power line is suspended between 2 points at the same height as shown here, then it takes the shape of a curve, again like this one, like a heavy cable across these two towers, same height. And then it can be proven, which I will do in this video, that this equation, or this is basically called a catenary, and this function has a formula y equals c plus a hyperbolic cosine h x over a, like that. Yeah, so this is a catenary function, and that describes this kind of shape when you have a heavy cable, or just a cable with a mass that sags like this across, and that's the shape it will or that's the equation that it will have. And again, recall that hyperbolic cosine is basically hyperbolic cosine of h is equal to e to the x, by definition, plus e to the negative x over 2. And you can learn more about hyperbolic functions in my earlier videos, and put that in a link in the description below. And so this curve is called a catenary, and basically the Latin word catena means chain, hence you have the chain like that. And also note, other formulations of catenaries are usually written as y equals to y equals hyperbolic cosine of ax over a, or you could write this as, I'll square this, or y equals to hyperbolic cosine ax, like that, over a plus another constant c. But I believe this one is the more common one, like here. But these are pretty much the same. All it will change is you'll have varying values for these constants c and or a. A and or c, like that. Alright, so now let's start looking at the proof for this. So since the calculus book that I'm following does not cover the derivation of the catenary formula, instead I used the following website for reference instead, although my method is a bit different than that used in the website, because I go in more detail and do things a bit differently. And this is the website proofwiki.org, equation of a catenary, and they prove this formula, or they focus more on that, but I will use that proof but then obtain this formula. All this is actually just switching how this a is defined, like that. You could just let a equals 1 over a, it just becomes something like that. So anyways, let's just jump right in. So in any of these box text forms, that will be that'll be when I'm quoting from this website. Otherwise, it's going to be from my own writing, like this one. So let's first draw a catenary with a catenary curve with the lowest point crossing the y-axis, so that we have a symmetric catenary like this. So this is the lowest point, exactly like this, assuming those are exactly equal distance, and there is that lowest point there. So that's what we're going to do, cross the y-axis, so that is we'll have a symmetric curve. And now from that website, so let xy be an arbitrary point on the chain, let s be the length along the arc of the chain from the lowest point to xy. In other words, just the arc length from the lowest to that random point. Let w naught or w0 be the linear density of the chain, that is its weight per unit length. So again, assuming it has a mass, weight is a unit of force, and then divided by unit length, like meters, millimeters, whatever length you're using, and we'll assume it's just evenly distributed across the whole cable. So the section of chain between the lowest point and xy is in static equilibrium under the influence of 3 forces, And again, static equilibrium is a concept in physics if you haven't already learned this. I'll cover this in more detail later, but if you have already in physics class or whatnot, this will be a good refresher. Basically, the sum of the forces in any direction needs to be equal to 0 so that it's not moving anywhere. And what I'll do is I'll draw a free body diagram on it and then sum up all the forces, try to put them all together, and we'll see what happens. But again, I'm just going to jump right in it, but in later videos I'll go over introduction and more so on the physics of it. So let's go ahead and draw this curve out. So we have the xy axis like this, and there's the x, there's the y. So let's draw our catenary. So this is the lowest point here. Let's say we have a point there. The edges are somewhat equal. It should be exactly equal distance. Yeah, alright, so now that we have this cable like that, let's say we have an arbitrary point right over here. This is our x, y. And now this whole cable has a linear density of W naught. Again, it's just a weight over a unit length, like that. Yeah, and now this distance from here to here, well, this is just going to be S. So from the lowest point all the way to any point there, that's going to be the arc length S across. Yeah, so now what we'll do is I'll throw this over here and then zoom in on it, on that section, and then we'll draw a free body diagram. So I'll go over more detail on this in later videos, but a free body diagram again just draws all of the forces acting on it. So if we take this one and put it in just midair like this, we'll have, this is the lowest point like that. So at the lowest point, assuming that the force is always going to be tangent to the cable, because basically it's being pulled from both sides like that, what we'll end up having is at this point we'll have a load like that. We'll call this T0, tension at that low point, and it's going to be perfectly horizontal. And now here's the rest of the chain like this, and then we're going to assume this is a tangent force, and I'll write this down here. So this is a tangent force, and for tension, tangent tensile force pulling that cable. Yeah, so it's tangent like that, and now this has a weight across here. So what I'll do is I'll draw a distributed mass all the way across, or weight. So it has loads pushing it down from every basically from every single piece of this chain, and then this has a intensity of it is, or linear density, W naught. So then if we were to sum this length up, and this again, this is the curve, this has a arc length of S. So then what we could do is multiply this S, which is in terms of the units are length, this one is weight per length. So multiply by that together, we get a total force, which is going to be at the center of gravity somewhere around here, and that's going to be a vertical downwards one, and that's going to be multiplied by each other. So density times it by the length, W naught times S. Yeah, so now the next thing we're going to do is use the static equilibrium equation. So this is in static equilibrium. Static means it's not moving, and equilibrium, what we have is, all the forces have to be 0 in both directions, and it will in all directions. What we'll do is look at the horizontal and vertical directions of the force. So we have a right here, the summation of all the forces in the x direction must equal to 0 so that nothing's moving, and these are all the forces acting on that piece right there. So the horizontal one, what we have is T0. This needs to equal to, well, the only other horizontal force is over here, the horizontal component of this right here, remember that's tangent. So what we'll do is draw a line like this. This is going to be the angle theta, and you could draw that right here. This right here is like that. This is T, and this is that horizontal component like that. Yeah, just draw this angle across. There's a vertical component, and again this one you could see it as dy over dx, and it's the same as the slope there. And the reason I'm writing the slope is because we'll use this later. So tan theta is going to be opposite over adjacent, dy over dx like that. So that theta, the dy over dx, is going to be the slope. We'll use this later on as well. So put that there. So that's tangent line. We have this now. This horizontal component right here is going to be this is going to be t. That's the hypotenuse cosine theta, and then the vertical one's going to be across there. This is going to be t sine theta. Yeah, because remember the sine is going to be opposite over hypotenuse. T is the hypotenuse, and this one's going to be whatever value, and you could just multiply it out and get t sine sine theta. The same thing for the cosine. So what do we have? That's the horizontal component there, and there's t0. So that means we have t times cosine theta. So now we have this equation. Now we sum up in the vertical or the y direction, so it has to equal 0, so nothing's moving. So we get, well, the bottom part here, W0 or linear density times S equals 2. It has to equal to the other vertical force. That's the horizontal vertical component of this part there, T sine theta, like that. And now because I showed tan theta equals to dy over dx, that's just a tangent line across there. Yeah, what we can do is, well, we can cancel this t out. That's just because that's just a generic tension at any of the points, or at that arbitrary xy point. So we can divide this by that, so we'll have a divide like that. Actually, put the arrows a different way. So we're gonna divide into this one there. Actually, it's a bit confusing, so let's just do this again. So I'm gonna do this divided by that. Yeah, so that makes a bit more sense. So I just wanted to show that visually there, like this. So that what we end up having is a W naught or W0 divided by T0, and then the top part is T sine theta divided by this part, T cosine theta. So these cancel, and then we're left with sine over cos, which is, well, tan theta, and this one we already know equals to dy over dx. Yeah, so now we have a differential equation, but before I write it down, I'm going to do is let a, just a constant, equal to these combined constants, W naught over T naught, which is that's a tension at the very bottom of the cable, and this one is just a linear density, like that. So then what we end up having is a dy over dx equals to a times s, and there's our differential equation. But now this s, remember, that's just arc length. So recall that s equals to arc length, and recall from my earlier video that the equation for arc length is just the integral square root 1 plus dy over dx squared dx, like that. So, but I don't want to work with the integral, so what I'll do is, and the reason I don't want it just makes it more complicated, we notice that there's a dy over dx and there's dy over dx, so we'll just take the derivative of this. So ds over dx, the derivative is going to be the integrand inside, which is going to be square root 1 plus dy over dx squared, like that. Yeah, so we have this, and the reason now this is going to be useful is we can take the derivative of that again, so we'll have a second derivative. So what I'll do is I'll just write dy over dx equals to, this is our just basic differential equation, a times s, and now what I'll do is I'll take the derivative d over dx of this, and then d over dx of this, like that. So we're doing it on both sides, so we're not changing anything. Let's put it like this, d over dx, like that. So what we end up having is a d squared y, this is the second derivative of dx squared, equals to, the a is just a constant, take it out, ds over dx, like that. Where ds over dx is just this part there, so we put that in, so we get a times it by square root 1 plus dy over dx, like that, squared. And now to simplify it so we don't need to work with this dy over dx nonstop, I'm just going to write this as let p equals to the derivative dy over dx. So if that's the case, then this is just dp over dx. So we get a dp over dx equals 2, and then that just becomes p in there, a times square root 1 plus p squared. And now we can try to evaluate this by, well, separating this into, move the p onto the p side and take an integral, move the dx on that side. So what we get, we separate the variables, we get a 1 over square root 1 plus p squared dp equals to a dx, like that, and then take the integral from both sides. Yeah, now what we have is these two integrals. The one on the right is pretty easy, that's just a constant, but one on the left, that's not too straightforward. And now to save time in solving the integral on the left, I just use an online integral calculator, just because it will take much longer to do this video otherwise. And that's right here. So the square root, the integral of 1 over square root p squared plus p, or 1 plus p squared, same thing. dp equals to ln absolute value square root p squared plus 1 plus p, like that. I will solve this manually in a later video, so stay tuned for that. And this is just c1. I'll call that c1. And then the one on the right here, the integral right here, that's just a constant, that just equals to ax plus c, and I'll call that constant c2, like that. Yeah, and now also note that this has an absolute value sign, but note we can remove that absolute value sign because, well, we know that square root p squared plus p, yeah, this is, well, greater than just square root p squared, because that has an extra 1 there, and it's always constant, and everything in the square root needs to be this is always positive. Anything in the square root needs to be greater than 0. So then this is going to be greater than, actually not greater than, this part right here equals to absolute value of p. Yeah, so then this means that because this part right here is always going to be greater than the absolute value of this, and this is always going to be positive, yeah, then basically this whole thing inside is going to be greater than or equal to 0, so it's not going to be negative ever. Because if this is negative in, let's say, a negative number right here, this is always going to be bigger than that absolute value, and that's going to be positive, so you can't, they'll just cancel, you won't have a negative. So thus, ln absolute value of square root p squared plus p, like that, is just equal to, and then put the plus c1, equals to ln of, ln, just normal brackets, p squared plus 1, just get rid of that square root, plus p, like that, plus c1. So, so what we have now is, now we just put that together, ln square root plus p, square root p squared plus p, plus 1, plus p, like that, plus c1 equals to, and now this above integral right there, ax plus c2, combine this one over onto that side, we get a ln square root p squared plus p equals to ax. I'm going to write this as c3, like that, where c3 is just equal to c2 minus c1. It's just still a constant, like that. I'll just put a bubble around it. And now this constant, we could solve that constant, because notice that if you scroll up right here at this point across here, that's just a horizontal tangent across there, like this. So this tangent there, y prime equals to 0, or dy over dx equals to 0 there. And remember, dy over dx is just, well, p, like that. So, and that is at x is 0 there. So we can write that down as, let's scroll back up here. Yeah, so I'll write note at, actually I'll erase this line as part of it. So note at x equals to 0, what we have is dy over dx equals, so remember that p is just equal to dy over dx equals p equals to 0. So we could plug that in, we get ln of square root 0, 0 plus 1, so let's write 0 for completeness sake, 0 plus 1 plus 0 equals to, well, 0 plus c3, and what we end up getting is that's just 1, square root 1 is just 1. So we get ln of 1 equals to c3, but recall that ln is just looks something like this. If this is x, that's ln x. It looks something like that, where at this point is 1. Here, this is ln, yeah, that's just ln x. This is 0 right here. So at the point 1 is 0, so this c3 equals to 0 like that. Let's put this recall over there. Circle this. Yeah, so thus we have it simplified. We got rid of that constant. Now what we're left with is ln of square root p squared plus 1 plus p equals to ax, and the c3 is 0. So now what we can do is take the we'll take both of these as powers of e. So we go e like that, exponentials to get rid of this ln. So the ln cancels. What we're left with is square root p squared plus p like that. And now what I'm going to do is I'm going to separate this like this and move it across here, equals to e to the ax. And the reason I'm doing that is to save time, because there's going to be a lot of algebra. I just wanted to save time, because what we'll notice here is this is what we're left with, and what I want to do now is multiply this by the conjugate. I believe that's what it's called, which is going to be square root p squared plus 1 minus p here, so that we can have some cancellations, especially that giant square root over there. And then just do the same thing on this side, so we're not changing anything. P squared plus 1 minus p, like that. And then FOIL this out. This by this is equal to, multiply that out, is just going to be p squared plus 1, and then that by this, that's going to be negative p square root p squared plus 1. And now this by this, that's going to be plus p square root p squared plus 1. And then we have p and negative p, so we have negative p squared. The reason we did this again is so we can cancel this part right there, so that the square root's gone. And now on this side, this just equals to eax square root p squared plus 1 minus eax p. And now what we have is this p squared cancels with this one right here. Now we have a 1 there. Yeah, so we have a bunch of cancellations, which is pretty useful there. So now we have a 1 equals to, over there, eax square root p squared plus 1 minus eax p. And now what we want to do is move this over, and then we're going to do square both sides, so we get rid of the square root. So what we get is a 1 plus eax. So again, this is just going to be a lot of algebra. Eax p like that. And then equals to, on this side, eax square root p squared plus 1. Now we're going to square this, we get here, just expand that out. Now we get a 1 times 1 plus 1 times this, eaxp. Then eaxp times 1, like that, is just going to be, well, now we're going to have 2 of those exact same ones. Now this times it by itself, plus e. Now it's going to be 2. We just put a square there, and then p squared over here because we squared it. Now on this side, we just square that, e 2ax, and then this square root cancels. So we get a p squared plus 1. Now we can expand this part here, e 2ax p squared plus 1 there, just e 2ax. And yeah, that just it like that. But notice here, this is the same as this one, e2ax times p squared, like that. And then there's p squared. Those cancel, so what we're left with is 1 plus 2eax p equals to this part here, e2ax, like that. Now we can move this over to this side and divide it out. Yeah, then divide this part out. So what we get is p equals to, move that over, yeah, e2ax minus 1 divided by 2 e ax, like that. Yeah, so now we could divide this out inside. This equals to e, and now 2a, we're going to leave the 2 there, so put the 2 there. E to the power 2ax, and then this is going to be subtracted by ax. So we have a 2ax minus ax, then minus right here 1. This is just going to be e. We're just dividing this part out, leaving the 2 there. This is going to be e to the negative ax, like that. Or you can view it as this is just going to be e to the 0. So you could be e to the 0 equals 1, and then this is going to be 0 minus 1. So same thing like that. E negative ax is the result anyway. So then what we get there is p equals 2. This is just going to cancel. We're just going to left with ax. So we have 2ax minus ax is ax. So we have 2 ax minus e negative ax over 2, like that. Now this is what p equals to, but we know that p equals to the derivative dy over dx equals to, yeah, right here, e ax minus e ax, like that, over 2. Actually, instead I'm going to write this is equal to dy over dx. So what I'm going to do is move the dx on that side. So what we end up having is a dx, like that, and then a equals to a dy. Just so we can take the integral, so we integrate this all out. Yeah, so what we end up having is y equals to the integral, because yeah, dy, the integral is just y. The integral like this, I'm going to take that 1 over 2 out of there. That's just a constant. Now integral of e ax minus e negative ax, like that, and then dx, like that. Those are just constants. The integral of e is just is itself, so 1 over 2, and now what we have is a e ax is itself, then divided by a for chain rule to account for it. Yeah, like that. Now on this part here we have a minus, e is going to be the same thing, e ax. Now divided by a negative a, the negatives cancel, becomes positive, like that. And then we always have to add a constant. I'll just call that c. Yeah, so now we can collect these. This is a common denominator is a there, and also move in the 2 there. So we get is y equals to e ax plus e negative ax over 2a plus c, like that. And now again, recall from above that this is just, well, we know that a hyperbolic cosine of x equals to ex plus e negative x over 2, like that, over there. So then this just means, in our case we're just using hyperbolic cosine ax. So what we get is y equals to actually like this, hyperbolic cosine ax. The only difference is there's an a over there, ax, and then we have to divide by this a, like that, then plus c. Yeah, so this one is the format that the that website uses it, but I'll just type this as equation 1. But you could also rewrite it in differently. Note, yeah, my calculus book my calculus book has it written as y equals to a hyperbolic cosine, and now we have an x over a. It just doesn't, because some people like it divided by a, someone divided by a inside that hyperbolic plus c over there. And it's the same thing, it just means the different values of a are going to happen. And this is 2. And yeah, these formulas are equivalent, and the constant a will just have different values, and you can even see this from above if you do a, for example here, yeah, like that. If you just let alpha, for example, equals to 1 over a, and actually, yeah, the other way around, you can just move that around. Let a equals to 1 over alpha, so you can just put that inside. We get a y equals 2, and then this is hyperbolic cosine of now x over alpha divided by, well, 1 over alpha is going to go over there, plus c. Yeah, like that. Yeah, so it's exactly the same thing here, and you can just let alpha equal to a, etc. And the same thing. Let's write this down. Same thing, just using a different variable doesn't change anything. Same thing. Like that. Yeah, now I just want to go over a brief historical note, just a pretty interesting history behind the catenary according to that website that I referenced in this proof. So historical note, the problem of determining the shape of catenary or of the catenary was posed in 1690 by Jacob Bernoulli as a challenge. It had been thought by Galileo to be a parabola, and Huygens showed in 1646 by physical considerations that it could not be so, but he failed to establish its exact nature. In 1691, Leibniz, Huygens, and Johann Bernoulli all independently published solutions. It was Leibniz who gave it the name catenary from a letter that Johann Bernoulli wrote in 1718. The efforts of my brother were without success. For my part, I was more fortunate, for I found the skill. I say it without boasting. Why should I conceal the truth? To solve it in full, it is true that it cost me study that robbed me of rest for an entire night. It was a great achievement for those days and for the slight age and experience I then had. The next morning, filled with joy, I ran to my brother, who was still struggling miserably with a Gordian knot. Interesting, gotta check that out. Without getting anywhere, always thinking like Galileo that the catenary was a parabola. So yeah, it's not a parabola. Stop. I say to him, don't torture yourself anymore trying to prove the identity of the catenary with the parabola, since it is entirely false. It's pretty interesting level of excitement over mathematics. So, however, Jacob Bernoulli was first to demonstrate that of all possible shapes, the catenary has the lowest center of gravity and hence the smallest potential energy. This discovery was significant. Now, this is actually a quite amazing feat, but it makes some sense because there's barely anything affecting the cable that's just hanging on two things, so it should form a shape that is basically the low energy on it, just gravity pushing it down. In other words, lowest amount of energy to make that shape, and hence that small potential energy. I may look into this further, which is quite amazing. Anyways, that is all for today. If you learned from this pretty extensive proof video on the catenary and that historical note, it was a very interesting history lesson there. According to that website. Anyways, that's all for today. If you learned, and like always, you can download these exact notes in the link in the description below it, and I will be uploading this to Steemit in article format shortly after I upload this video, so check that out. Anyways, thanks for watching, and stay tuned for another Math Easy solution.